So this is the video for limits day 1. This first problem really you should already know how to do because this is an infinite limit, a limit as x approaches infinity, really large value of x, or you can think of this in terms of end behavior. Since the degree of the denominator is larger, we know that this limit equals 0. Okay, this is to enter it into the calculator and to look at the graph in the table. Now this is a tool we may use from time to time in this new part of limits. So I want you to see I have this typed into y1 and I have a nice window, it's graphed. We can see clearly that as x approaches infinity, y approaches 0. That's because we have a horizontal asymptote there. And if I go to the table, I can see as x gets bigger and bigger and bigger, y is getting smaller and smaller and smaller, approaching 0. Alright, so that's a technique you may want to use in this next part of limits because we're going to break it open. So this says if f of x becomes arbitrarily close to a single number L as it approaches c from either side, then the limit of f of x as x approaches c is L, meaning that this right here doesn't have to be infinity anymore. It could be a limit as x is approaching a number, alright, and then we're just going to use L as the limit. Okay, let's look at some examples. So in number 1, we have the limit as x approaches 0. Now if you're given something really basic like a linear or even a higher order polynomial, okay, all you really have to do is plug in the number, but I want to show you what happens in your calculator, okay? So let's go in to y equals, and let's put in 5x minus 3. And we can look at the graph here, zoom 6. And I want to know what's happening at 0. At 0, clearly, from both sides, the y value is approaching 3. We can look at it at the table as well. Okay, so I need to scroll up here, back up to 0. And you're going to notice that from this side, we're approaching negative 3, and from the top and from the bottom, or really from the left and from the right on the graph. Okay, so we're really sure that this is negative 3, and that makes sense because, like I said, went ahead and kind of told you the end of that story is you can just plug in that number. Now, some other functions are going to cause you some problems. All right, so let's think about what this would be for a polynomial. So we can plug it in. This is going to be 4 minus x cubed. And we can do a zoom 6, and what we're looking for is as x approaches negative 1, we can see clearly that this graph is continuous. That's important here. It's doing the same thing from the left and from the right. It's converging basically at a single point. Okay, you can look it up on the table, and you can also just plug it in. So 4 minus negative 1 cubed, this is going to equal 5. Alright, so what do you think number 3 will be? You can either use your calculator or you can just plug it in. Plugging it in at this point is probably easier. And that's going to give you 27. Okay, so here's the thing. If f of x is continuous, and we know what continuous means, it means the slang definition would mean you can draw it without picking up your pencil. Alright, then f of c is equal to your limit. Now if f is not continuous, then we'll deal with that in a minute. Okay, so in general, the limit as x approaches r of p of x equals, let's use the notation here, p of r if p of x is continuous. And I'm going to add a little, or so it seems. Okay, there's even some issues here that we will see. Limits kind of can get hairy, but for just your basic linear or polynomial graph, plugging it in is fine, but we always want to have the backup of our calculator in case things get weird. Okay, so we look at this next problem. All right, this is not a continuous graph, so I know that I can't just plug into, and in fact, if you were to plug into, okay, if I consider this to be f of x, and I plug in, if I consider that to be f of x, then f of 2 is actually equal to 0 over 0. And 0 over 0 is an interesting number. Is it 0? Is it undefined? Well, with limits, This is even more special. This tells us something interesting is going to happen. Okay? So I don't really care that f of 2 is something I don't know. I don't care. I'm just looking for as x approaches 2. Okay? So if we look at this on our calculator, if we plug it in, and we obviously could graph this by hand. I'm using the calculator here just to kind of speed along the process. So what we're looking for is near 2. Oops, did I type that in right? Oh yeah, okay. So we were expecting a rational, but we got a line. But at 2, if I were to do trace 2, there's no y value. What's at 2? It's not showing it here on the graph, but if we were to graph this by hand, we would have plotted a hole here. Okay, so algebraically, let's think about why this happens. All right, so I'm going to rewrite this as the limit as, not n, as x approaches 2, and I'm going to factor. This becomes x minus 2, x minus 5. I don't know why I put all those parentheses in. We don't need those really. X minus 2, x minus 5 over x minus 2. Okay, and I can clearly see, okay, that was what's causing the hole. So it wasn't really an asymptote, which would be a whole nother thing, but we'll work our way up to that kind of thing. And so really what I have here is the limit as x approaches to just of x minus 5. So this looks like what it was on the first page, where we just plug in 2, and 2 minus 5 is going to give me negative 3. So even if at, let me just read the statement because I think this says it really the best. It says the value of the limit is related to the behavior of the function near x equals 2 and has nothing to do with the function at x equals 2. F of 2 here was undefined, but the limit still had a number, and we saw it on the graph and we saw it algebraically. All right, let's do a couple of these where we're given the graph, so this will be a little bit easier, I think. So here we have the limit as x approaches 2. So we can see that this is kind of like the one we just had where there's a hole at 2, but there's an actual point down here. All right, so I want to be real clear here. F of 2 is not 1. It is negative 2. Okay, when x equals 2, y equals negative 2. But the limit as x is approaching 2 from the left and from the right approaches the value of 1. So my limit is 1. So notice the difference here. Okay, here we have the limit as x approaches 2 of f of x. Okay, well, this is kind of weird because as x approaches 2 from the right and as x approaches 2 from the left, I get two different numbers. Okay, when you get two different numbers, this limit does not exist. Okay, we saw that with our infinite limits when we were bouncing back and forth between a positive and a negative. All right, limit as x approaches 0 of f of x. Okay, now we're to a continuous one. Okay, before we were not continuous, so we knew those were going to be weird, but this one is, so it seems continuous, but there's a lot of oscillations. I'm really not even sure what's going on here. So it looks that I'm close to 0, but you're really not. It's oscillating so wildly that I don't even know what's going on. And so a safe answer here, and the true answer would be does not exist. Okay, we'll explore this more. So if you have a little bit of questions on this, that's okay. We call this oscillating. All right, number 8, we have the limit as x approaches 1. Now this is a continuous graph. It's a parabola, so I should have a really basic limit. And I do right here. As x is approaching 1, both from the left and from the right, the y is approaching 1. So it's the same number from the right and left. Okay, so we see these are 4 very different problems, and we've got some idea of when a limit exists and when it doesn't exist. So on the next page it says limits that fail to exist. Now we know why they fail to exist when we're talking about infinite limits, but this is where we have a number here. Okay, what if the behavior differs from the right or from the left? That was like number 6. Okay, That limit failed to exist. Okay, this is another one where the limit fails to exist. Okay, if I draw this, I'm not going to take a whole bunch of time to explain the graph here, but we have a graph going that way. We have a graph going this way because of the absolute value. It's +1 for all the positive x's. It's -1 for all the negative x's. At 0, there is no point at all. So f of 0 does not exist. Now, if we were approaching the same number from the right or from the left, we could actually have a limit, but this is why this limit does not exist. It's not because of what's happening at 0, it's because what's happening on the right and what's happening on the left is different. Okay? So now we look at this one. Does the limit as x approaches 5 of this same graph exist? Well, yes. 5 would be over here. We'll just call this 5 right here. Yes. And if I switch my colors up, I can see that from the left and from the right, it's the same behavior. Okay, so yes, and that would be 1. And we can see clearly that absolute value of 5 over 5 would equal 1. All right, now let's talk about unbounded. Unbounded means we're going off into infinity. Okay, what would happen if we just plugged in 0 here? You would have 1 over 0. All right, so that's weird. We know that's weird. It doesn't mean a limit can't exist. It just means that it's a little bit trickier than just plugging it in. All right, so let's think about, this is a parent function, and you should kind of know what this looks like. This is what it basically looks like. Rough sketch. We've got asymptotes, both axes, and as x is approaching infinity, or sorry, as x is approaching 0, the y value is approaching infinity. Now, I see how you're saying it's approaching infinity on the right. It seems like the same behavior, but this is another limit that does not exist, okay? When we were talking about infinite limits, we can have infinity as an answer, but these are, so to speak, finite limits. These are limits as x is approaching a number. If your end result is infinity or negative infinity, that limit does not exist, okay? It says by choosing values of x close enough to 0, you can force f of x to be as big as you want. Because f of x is not approaching a real number, we said L was going to be an actual number, the limit does not exist. So end of the story is, if x is approaching a real number, you've got to have a real number answer. If x is approaching infinity, like what we saw last chapter, your answer could be infinity. All right, I will answer questions about that in class because I know you might have them. All right, oscillating behavior. This is like number 7. And this graph, I'm going to actually graph on the calculator and show you kind of how weird it looks. Okay, so here we have, because this is really hard to draw by hand, that's why I'm doing it on the calculator. Okay, so we have sine of 1 over x. I'm going to go ahead and be in radians mode, yes I am, and I'm going to hit zoom 6. Alright, so we see some weird stuff going on around 0, so let's zoom in and check it out. I can see what the end behavior is, and it looks like 0, 0 is a point. Is 0, 0 an actual point? Well, it looked like it was, but when I actually trace to it, I get another blank, okay? So that's because if you plug in 0, 1 over 0 is undefined. You can't do sine of 1 over 0, and you can't really even say that this is infinity, which some of you might be thinking. Okay, so why don't you sketch this graph just so you have it on your notes. It's like some weird stuff. This limit just does not exist. It's oscillating too wildly. And the more you would zoom in on your calculator, the more you can see how strange it is. It's just really hard to tell. And you could keep zooming in and see some interesting things. All right? Even though it appears that it's doing the same thing from the left and the right, it's oscillating, so this limit does not exist. We did not have to deal with this with infinite limits of last chapter, but we do have to deal with it in this chapter. Remember, the limit of as x approaches c of f of x does not depend on the value of f of x equals c. All right? They might be the same if it's continuous and if it's a basic graph, but they don't have to be the same. It doesn't determine whether the limit exists or not. All right, so let's compare and contrast this f of x and g of x, okay? If we're looking at limits, okay, let's think about and I want you to change, I'm sorry, I want you to scratch this out. Scratch that off your notes. It may actually already be fixed on your notes. I'm not sure. But I want g of x just to be x plus 1. All right, if we simplify f of x to be x minus 1 times x plus 1 over x minus 1, and we cancel, it appears that they're the same. What's the main difference then? Okay. Which one has the whole? Okay, f of x has a whole where? It's at positive 1 and then 2. That's the only difference between these two, okay? So when you're thinking about f of x and g of x, and I'm asking you to find the limit as x approaches 1, as the limit as x approaches 1 of f of x, which you can really consider is the limit as x approaches 1 of g of x, which ends up being x plus 1. And these two are almost identical graphs. It's just one has a whole, all right? That will not affect the limit. So what does the limit equal? 2. All right. Now the next one, it looks like it's the same problem, but this is a little bit different here, okay? So we're going to have to go back to the beginning, and what we're going to do is we're going to factor the numerator. The numerator is going to be x minus 1, x plus 1, and the other term is going to cancel here. X plus 1 is going to cancel. So this would be the same thing as the limit as x approaches 1 of x minus 1. Okay? This line does not have a hole. The original graph had a hole, but again, it doesn't matter. Okay, we're just talking about the limit, the values near x equals 1. So now that we have something that is continuous and basic, I can just plug in my value. And these are how you do limits, especially when they're not continuous. Okay, so some functions obviously do not have limits. You can tell ahead of time if manipulating the equation will allow you to find a limit. If direct substitution, which is kind of what we were doing before, with continuous graph, if it yields 0 over 0, this is called indeterminate form. It means that the limit does exist, but the function is currently in a form that causes the limit to be indeterminable. So 0 over 0 is actually a really good thing. That means the limit exists. We just have to do a little bit of work to find it. So on this number 11, if you were, if I consider this to be f of x, then that means that f of negative 3, you can do all the number crunching you want, is going to give me 0 over 0. I can see this more clearly when I factor it. So this would be x plus 3, x minus 2, over x plus 3. And I can see that plugging in a negative 3 gives me 0 over 0. We know this to be a whole, and a whole will not affect the limit. Okay? Asymptotes there, if I had just had 0 in the denominator, just had a vertical asymptote, that's different, all right? But this is a whole, this is not affecting the graph. It is affecting the graph, but it's not affecting the limit, okay? Once you simplify it algebraically, you can get the limit. Now, sometimes it's not always as simple as just factoring and canceling out the whole. There are going to be harder problems, but the whole idea here is 0 over 0 means the limit exists. We've just got to do something to it, okay? So let's think about this next one. All right, if I factor this, and factoring this is another reason why we are always on you guys' case about learning to factor. You got to be really good at factoring to do all of this limit stuff. All right, this is going to be x minus 5 x plus 2 all over x plus 5. Now nothing cancels here, so plugging in a negative 5, actually it seemed like it should. It was almost too tricky. It caught me off guard even though I have my notes right here. So if I plug in a negative 5, this is going to give me some number over 0. This is when the limit does not exist. Okay? Now, just for fun, be thorough, let's pretend this minus 3, let's just change the problem, let's make it a plus. How would that change my factoring? Well, it would have made that plus and this minus. Okay? So what this means is then the x plus 5s would have canceled, which would have been a whole. That then would have been the limit as x approaches negative 5 of x minus 2, which I can plug in because I now have something that's continuous and basic, and that limit would have been negative 7. So hopefully you see the difference between 0 over 0 and a number over 0. Okay, bring your questions to class.